Yeah,
Yeah,
you'll see it. Okay.
Okay, and it's my pleasure now to pass the mic to another speaker, Mille from Spain, from University Pompeu Fabra, from Barcelona. So Simon is conducting his studies in natural language processing, right?
Yeah.
So and today he's probably going to share some his insight on this. If everything works.
If it works, yeah.
Yeah, yeah. So basically, he would say a few couple words about like his studies and himself by himself, right?
Yeah.
So yeah. So now I'm just like passing the mic to him.
Thank you very much, Constantine. So, hi everyone. How many of you know about computational linguistics or natural language processing? Ah, okay. More than I thought. That's great. So as you know, like now we just had a talk about memory, so about how to access memory. Now this thing is more about how we get to store stuff in memory and how we get to use it, which is like understanding language and producing language when we talk. So so I'm gonna present briefly like what I'm doing in my group in these days. Then we'll see how like linguistic frameworks can actually help processing the information, be it for analysis or generation. I'll give a few examples about recent shared tasks that happen, international shared task competitions with different systems, so we can compare the results of different types of systems, and I'll conclude. So in this presentation, we'll see two types of examples only, so I limited myself to air quality domain examples on the one hand, and also DBpedia triples, so that what's behind Wikipedia, all the information that's behind Wikipedia. Why? So the title is again like what about the linguistics in computational linguistics? The idea is that, as you know, in NLP and in other fields now, it gets very neural, no? Neural networks everywhere, black boxes that are mysterious to me, magical. I'm a linguist in the first place, so I'm not attracted to these kind of technologies, but they work really, really well. So lots of people do research in the neural stuff, and we tend to forget about, I think, more linguistic approaches that are, that encode like the linguistic properties that we have in language. So in the recent events, there's been some interesting findings in these areas. So I thought, okay, let's try to do a bit of, 3/4 of an hour on this topic and try to see where this linguistic information can actually be useful. I work now in UPF in Barcelona. So we're in a small university, just 25 years old, small one, 10,000 students with 600 teachers, more or less. The topics that we tackle there is like computer science, telecommunication, audiovisual technologies, biomedical engineering. So we have 22 degrees, 25 masters around these topics. In this university, there's like in this department, we have different groups in these topics, and I am in the natural language processing group, obviously. We have 3 labs there. I'm in headed by Leo Vanner, Horacio Sajon, and Mireia Farus, respectively. I'm in the knowledge-based natural language interaction lab. So in this lab, we do stuff like syntactic semantic parsing, concept extraction, conceptual extraction, population of ontologies, so structured knowledge representations, author profiling, stylistic profiling, so how people write, how it correlates with their profiles. We do summarization, report generation, so personalized, targeted to different users. Interactive communication, which is like the development of communication agents and stuff like that. Computational lexicography and data annotation as well. The other 2 labs, so the first one is more centered on summarization simplification, sentiment analysis, and Mireia's lab in speech technologies. So today, we'll stay here. I work mostly in semantic parsing, concept relation extraction, and report generation. So this topic here and corpus annotation will be revolving about these 3-4 topics. To give you an idea about how we apply all this in real life, so now we have currently 5 or 6 European projects that are running. We have 2 we are working on two projects that are about automatic generation of 3D models. And NLP here can be used to analyze the needs of people to get a particular model, so be it for designers or architects or for as an artistic expression. And also we use these NLP technologies to generate reports that can, for example, describe an automatically generated 3D model. So the one who's going to use it knows what it is about, where it comes from, its properties and stuff like that. We also have a couple of projects about security, and this is going to be annoying. Where in this case it's about detecting terrorist activities online, so on the dark web, see who is maybe like trying to plan terrorist attacks, and see who is hiding behind profiles that can be aggressive. And here then, so it's like a statistic profiling, and also try to make some reports about all this. We also have a project about helping the first responders to act in case of a crisis. So if there's a flood or a heat wave or fires, so lots of people post stuff on the social media. We can analyze what's happening there, the images and the text, and then send a little report to the authorities, trying to give an overview of the situation. So that's for the context. So now we're gonna go a bit deeper in the topic of today. So as you know, language processing. So you can start with sentences. Now I don't know if you see very well, but so you have two sentences here. One is because of the moderate wind, there is a lot of alder pollen in the air. The second sentence here is the moderate wind will make the alder pollen concentration abundant in the air. So these two sentences are quite different, but you can see that they mean exactly the same thing. You can have a very long list of sentences that mean the same thing in English. You can have some in Russian, in French, in Spanish, in whatever language. You would have thousands of sentences with different words, different forms. They have to be understood. And by understood, I mean we have to get to some kind of abstract representation underlying these sentences. So on the one hand, we have like thousands of sentences. On the other hand, we have like one common meaning representation. So this is what could be a conceptual structure. Okay, it's not like formally defined. It's just it's an intent. Okay. So you see here. So we have relations of like rating. So the wind has a rating that's moderate. Pollen has a certain type that's older. Also has a rating. And this thing, that the moderate wind, is causing this thing. So if I analyze all these sentences, I would like to get to this abstract representation. And the other way around, if I have this as input, I want to be able to produce sentences like the well-formed sentences like this, starting from this kind of abstract representation. So NLP is about going both directions, no? From the text to the abstract representation, and from abstract representation to the text. And you see that the gap is quite large. Okay, now it's not very obvious because it's the same language, so you have lots of words that are found here. But for example, the cause here is not verbalized. The types, the ratings are not really verbalized, but they're contained in these sentences. So the idea is that, okay, you could try to do that in one shot, analyze here to here in one shot, or to here from here to here. I don't think it would be very successful in most cases because, yeah, the gap is too large. So that's where the linguistics come into play. Instead of doing that in one step, we can do it in several steps, like minimizing the gaps between two consecutive structures. So, no. That's going to be very hard for you upstairs to see, but I'm going to tell you what happens here, okay? So if we start from the text, the first level is like a morphological analysis. So we say, for example, this is because of the moderate wind. Wind is singular. There will be infinitive, a lot of other singular pollen. So here we make explicit the morphological information. That's the first level of abstraction, quite close to the text still. We don't go very far. The next step would be to get a syntactic structure of the tree. So you can say that because of are linked by a certain relation. The air is also linked by a dependency relation. These here relations connect all the words of the sentence, so we're still close to the original sentence. I took the first one as example, because of the moderate wind. there will be a lot of other pollen in the air. These small relations here, so this one is called det between air and d, and this encodes linguistic properties. So in English, this det encodes a property that, for example, linear order, the determiner will be before the noun. In French, I'm French, for example, I would say that this det relation will encode not only the order, but also an agreement between the noun and the determiner. So through this relation, the determiner will get its number and gender from the noun. In other language, I think in Russian maybe you have cases, right? Yeah, so you would have also case propagated through certain relations, not through other ones. So all these relations are language specific, and they encode properties that are language specific. Okay, let's try to abstract a bit more. So now we try to abstract from the very language specific features. So these determiners, you don't have determiners in Russian, do you? Or there are some, but not all of them. I don't know Russian enough. I'm just making guesses. But in languages, you don't have determiners. In some languages, you don't have auxiliaries, like will be. The tense is just expressed as a morpheme. We call like an inflection on the verb. In some languages, you don't have prepositions, like because of the wind. You have cases. So if you want to abstract from all these features, you have to go. You have to remove all this information and make it to make it less important in the structure. So here we go from a tree with all the words to a tree with only the content words. So the of has gone, the has gone, the will has gone, and the relations that were here encoding language-specific properties, they will be generic and language independent. So now we go towards a predicate argument structure. I'll show you maybe a better example just afterwards. I'll explain what these 1 and 2 means. Here we abstracted from the words, from the surface relations between the words, but we still have the sentence structure. This is again something that's quite superficial, and we want to also be able to abstract from that to get to this conceptual structure that we saw at the beginning. So here, see, this be is here in English only because in a sentence in English you need to have a verb. It's actually an empty verb, this one. So if you want a semantic representation, you won't represent that be because it's just here in English to make that sentence happen. So removing that be, you're left with meanings like, okay, so this because, this word because becomes a meaning cause. This moderate can be a meaning called moderate, so wind is also a full word. And then you see, so this predicate arguments, so moderate has one argument, wind, because adjectives are predicates in a sense that they need something, they apply to something, no? Moderate, something is moderate, blue, something is blue, etc. Cause would be a predicate with 2 arguments. Something, someone causes something else. So cause has 2 arguments, the wind being the first argument, the most important one, and the second one being what is being caused. What is being caused is a large quantity. Again, predicate with 1 argument of what? Of pollen, etc. So here you abstracted from the sentence structure, and it's good. So now we got really close to the conceptual structure we saw at the beginning, and it's so that's the way we want to go. These things, these bubbles are like there's different theories about that. It's like the information structure on top of the of the semantic structure. So the theme is what you talk about. We talk about the ardent pollen. The rime is what you say about the thing that you talk about. So we say that there's a large quantity of it. And the specifier is extra information. If with the same structure you would take, you would say, for example, the wind is the theme and moderate is the rime, and all the rest is additional information, the sentence could be like, the wind is moderate, which causes that there is a large quantity of pollen in the air. So by playing with these parameters, you can really change the output structure, that the sentence that you would generate. So all these layers here, I didn't take them out of my pocket like this. They actually come from somewhere. There's a theoretical background on which all this relies. I don't know if you heard about this, meaning tech theory. Anyone? It's from here, from Moscow, from a guy called Igor Mechuk, who developed that in the yeah?
He's now in America, I think.
Yeah, he's in Canada now, yeah. he spent, he moved there a long time ago, but so he started working on the MTT here, and it's so he foresees all the layers of representation in a language. So his idea is a theoretical linguist, brilliant, of course, and he did this theory that so I'm going to just show you the layers. So again, we have the text, the conceptual layer at the two ends. So he has something called this surface morphological layer, which handles morphological interactions. We have deep morphological layer, where word order is managed and agreements between the words are managed. You have surface syntactic layer, which is the syntactic tree that we saw before on the right, with relations that are language specific about all the words. Going a bit deeper, we have the deep syntactic layer. That was the structure that was here, with still a sentence structure, but with abstract relations and only the content words. And then finally, he has this semantic layer, which was a graph that we saw at the top before. That's still language specific. It uses meanings of a specific language, but it abstracts from many things. And then this is easy to connect to something that would be conceptual, as we saw before. So this model, meaning text, is meaning to text. It's intended to be for generation, so from semantics to the text. But it can be used both ways. What matters here is that every layer is formally defined. So there's formal definition, and a translation between two layers is also formally defined. So based on these linguistics, you can implement systems that travel from one to another thing. So that's what we're going to see right now, how it works more into details. So for the linguist, just to have a needle, I put here semantic, surface, syntax, and text in bold because these are you have many theories in linguistics, okay? So these are the three layers that everyone agrees on. If you ask anyone about deep syntax, they're going to tell you, oh, that's really bad, it doesn't make any sense, blah, blah. It can happen. But semantics, surface, syntax, and text, everyone agrees. If you're familiar with NLP, you may know some resources. So just to situate a bit these layers with their typical resources. Surface syntax, you have resources like the Penn Tree Bank. This is the big corpus of English, the most widely used corpus of English nowadays. You have universal dependencies, this new multilingual corpus that's also arising. For the semantic layer, you have stuff like a prop bank, also for English and adapted to new languages recently. You have abstract meaning representations. So we've seen the meaning tech theory, semantic deep syntax. You have the tecto-grammatical layer of the Prague School in Czech Republic, or deep universal dependencies. Then if you go deeper again, so the conceptual / structured data, so it's not the same thing. This is more linguistic. This is more word representation, knowledge. So here you have stuff like ontologies, time series. Time series, what we saw, for example, as input for the meteorological domain. You would have, if you have sensors in the air, they can tell you temperature, wind speed, humidity. So this is data that's just time series. There will be items also, no, that are stored like this on some places, and then can be verbalized. We'll see that. So this is, in general, the format is like LDF triples for these ones. So we have these three things. Now the tasks, you understood, of course, that if you go from text to up there, we're talking about natural language understanding. So text to syntax is like syntactic parsing. Text to semantic layer is semantic parsing and semantic role labeling. And if you go up to the ontologies, it's ontology population. The other way around, going from this abstract representation to the text, we have the ontology verbalization. From semantics to text is called like surface realization. And surface syntax to text is more like just linearization and inflection generation. So next, we're going to talk. So this is the core of today's presentation. We're going to see in detail this step. So this natural language generation from structured data. And right after, we'll talk a bit about the transition between surface syntax and deep syntax, and semantics, sorry. So now, we're going to see some RDF triples from DBpedia and how they're verbalized into some text. So you all know Wikipedia, I suppose. It's a huge resource with lots of data. You have the text, okay, and on the right, so here it's quite at the bottom, you have this thing. This is the info box. It's called the info box, okay. So this is the page of Belgium. I'm really sorry. This is very, very small. Everything. If I had known, I would have made it bigger. But again, I'm going to comment on that. So here you have the info box says like capital, Brussels, official languages, Dutch, French, German, religion, so the percentages of the religion. You have the government, etc. No, the monarch, the prime minister, which is Charles Michel. So all this data here is based on DBpedia, on a set of triples. So the information is encoded into triples, like a subject, which is the Belgium in this case, a property, so capital, official language, prime minister, and an object. So the value for this property, so capital Brussels, German, Charles Michel, all these are this format is underlying these info boxes. There's billions of these triples on many, many domains, and this knowledge is kind of stuck up there. So there's kind of a need to verbalize this, to make the information available to many people. In this case, in the case of Wikipedia, most of this information is actually in the text, but in many cases, there's nothing verbalizing these triples. So that would be the input of our generator now. We're talking about generation. So we see these two we've just seen, Belgium, leader, Charles Michel, Belgium, language, German, so subject, property, object. I have like two other triples here related to Belgium, which is this time the object of country, so Antwerp is in Belgium, and something happening in Antwerp, which is the airport that serves Antwerp. Here we have four properties. The task is to generate a text. So here you have human references. So for these four properties, the first one is, so Charles Michel is the leader of Belgium, where the German language is spoken. Antwerp is located in the country and served by Antwerp International Airport. That's been written by humans, actually. The second one, Antwerp International Airport serves the city of Antwerp, which is a popular tourist destination in Belgium. One of the languages spoken in Belgium is German, and the leader is Charles Michel. Still good to me, although they added some information about like popular tourist destination. That's not really encoded here, but why not? Third one, Antwerp International Airport Services, between parentheses, Charles Michel, led Antwerp, Belgium, German is spoken here, 2 dots. I think this guy had maybe been partying before or something. This sentence is not really great, but I mean, you see, humans also sometimes produce sentences that are not good. So that can happen. Now, when you have thousands of these and thousands of these, you make yourself some training data, okay? Some data on which you can learn. And you can train systems to learn how to verbalize the contents here into texts that are similar to that. So that's been done by a group, a research group in Nancy in France. They created a big data set verbalizing exactly the contents of the triple. So you have thousands of pairs between triples and texts. And they made a competition saying people, okay, now we're going to give you all this data. Please make generators and try to get as close as possible to these reference sentences with your system. To verbalize the data, there's many different approaches. No? So the three basic ones are from maybe simpler to more complex. The first one would be template-based approaches. So this template-based approach, you see one property like leader, and you have a template. So the leader of X is Y, no? Subject is object. And then when you see a triple that contains leader, you put the value of the subject here, the value of the object here, and you have yourself a sentence that's well generated. Okay? This technique is kind of so you ensure that the output quality is good. It's kind of fast because it's just retrieving some template and populating it. And it's easy to craft. Like anyone can make these kind of sentences with placeholders, right? Cons, of course, the big con is like it's not scalable. If you want a different structure, you have to write a different template. If you want a different language, you have to write a different template. And very soon, very quick, it starts being impossible to manage. So it's good to avoid that. Then you have rule-based approaches. So these approaches will say, okay, if I see this property leader, I will trigger certain rules that are in my grammars. So for example, I will, in English, I will trigger a rule that introduces a support verb, like a be verb, like someone is the leader. I will trigger rules that introduce a relative pronoun if this leader is embedded in a noun group, so not the main verb of the sentence. I will trigger rules that make be agrees with the subject, as we've seen before, etc. And also that's triggering lots of rules that are pre-existing, that you have developed. So here, the pros is again, the output quality. You can control the output quality of your system with rule-based approaches. It's quite flexible because you can adapt to different kinds of inputs, and it's scalable. You can really, it's scalable. So the scalability is what allows you to adapt it to many different inputs, and flexibility in that it will not be as restricted as the template-based approaches. Cons, because there are cons, of course. They're a bit more costly to implement. It takes some time to encode all these rules, and these systems typically have coverage issues, which is if you have data that are not foreseen by the rules, the generator doesn't know what to do, so it kind of breaks. Then you have the more intelligent approaches, let's say, the machine learning approaches. In this case, this approach, like we'll see one property and of course the two subject and object, and we'll predict the most probable string of words given this property and the surrounding properties and the values. So just statistical decision. We'll create a little sentence. Again, black box. The pros here is like it's kind of faster to implement than the rules, because I mean many of you have done, I guess, already machine learning algorithms. It can be like you can do a whole system in a couple of weeks, or maybe faster. The coverage is great. So these systems adapt to unknown. If you have unknown inputs, they will still generate something. It will be wrong, but it will do something. The cons for me, of course, and for everyone, they're fully dependent on training data. If you don't have training data, you don't have good outputs. Also, the outputs can be unpredictable. These machine learning systems, especially the neural systems, they hallucinate facts. So they put in the output stuff that is not in the input. They invent themselves stuff. Or they can also tend to repeat some words and do some ungrammatical sentences. It can happen. So this is the basic techniques. Of course, you have combinations of all these techniques, so you can learn templates and then learn how to populate them statistically to make a sentence. You can use templates and then generate templates with rules. You can also combine rules and machine learnings for different parts of the generation pipeline. Of course, there's infinite possibilities, no? So as we've seen before, the distance between what we want to generate, the triples and the text, is quite big. So now we've seen the techniques, like the implementation way. Now we see like the methods to generate. So you have mainly two possibilities. Either, as I said at the beginning, you do it in one shot. So it's end-to-end approach. I have my triple set and I generate a sentence in one shot, or a little text. This is specifically good for machine learning approaches, or for maybe template-based in some cases. But there, of course, there's no room for linguistics. You just learn to produce something statistically, and that's pretty much it. Another approach is to do the pipeline approaches, which is to break down the task in several subtasks. So here, of course, you need intermediate representations. But we've seen that there are some linguistic models that define these intermediate representations. So that's great. So you know where to go. You're not lost, no, if you want to do these kind of approaches. And each transition can be done by rules, can be done by templates, can be done by machine learning. You can combine stuff here. It's not. It doesn't make. As you wish. So now what we're going to see now is I'm going to show you the results of two types of systems. I took the two extremes, the two opposite systems. On the one hand, we'll have neural end-to-end, so one-shot generation, neural-based. And so these are especially these two systems, Adapt and Melbourne. Adapt is the system designed in in Ireland, in the ADAP Center in Dublin, and Melbourne is, as the name says. And we're going to compare the results of these two neural systems with one fully rule-based system that's pipeline. So again, they're opposites because I could have taken a system here that does a bit of machine learning, a bit of rules, but it's just fully rules, fully neural here. So this forge system is the system that I developed in the past years. So it has grammars, it has lexical resources, and it's based on the meaning tech theory, as we've seen before. So you have an idea already of what an end-to-end system can do. I showed you have the input, produces an output. It's not much. I mean, I don't understand these things. I won't explain you how neural stuff works. But I can explain you how a rule-based system works. So we're going to see quickly how the generation is performed from these triples in the case of the linguistically informed generation. So again, we repeat the four triples: Antwerp International Airport, city, Antwerp; Belgium, leader, Charles Michel; Antwerp, country, Belgium; and Belgium, language, German. So this is the input. So in my system, I actually also use templates, but at a very abstract level, which is predicate argument templates. We've seen predicate arguments before. So for city, we have the serve predicate. So city was the one for an airport serving a city. Huh? So the subject served object. For leader, we have a predicate leader with the object being the first argument, the subject being the second argument. So this will be the guy and this will be the country. For country, it's will be a city that is in a country. So the subject is the city, the object is the country. And for language, we have speak, which is the predicate which has only the second argument. So someone speaks something usually. But now the someone is not there. We just have the something. So it's something is spoken and in a certain location. So these templates, then you can combine them according to how many there are and get a nice text. So we'll see how it's done step by step. The first step, of course, is to populate these templates with the values that we have in the input. So we end up with like Antwerp International Airport serves Antwerp, Charles Michel, leader, Belgium, Antwerp B, Belgium, and German language spoken in Belgium. So these are my little templates. If I generate that as such, we will end up with 4 small sentences. No? More or less like the 4 sentences that I just said now. This is not very natural. We tend to put stuff together when we talk. So first thing is to bring together triples that can be brought together. So here we have like Belgium, Antwerp is in common between these two, and we have Belgium in common between these two, and Belgium is here too. But this one is already busy with this bubble, so we're going to put these 2 triples together and these 2 triples together to end up with 2 sentences. What will be 2 sentences now? So one with the Antwerp, which is in Belgium, and that is served by the Antwerp airport, and then we have the Belgium, in which the leader is Charles Michel, and in which German is spoken. So we have these predicate argument structures, and now it's time to make it more close to the surface, as the opposite way that we did before. So defining the sentence structure. So in the first one, the system decided that serve was the main verb, and then unfolded the graph in the 3-way. And the second case, the B was decided to be the root of the tree, and then the graph again was unfolded like this. The nodes that need to be repeated, because Antwerp, for example, if it is served by an airport, but it's also in Belgium. You see that the structure before, we have just one node, no, for Antwerp and one node for Belgium here. In English, if you do this kind of structure, you need to repeat the word, no, like in a relative pronoun afterwards. And same for Belgium there. If you have this kind of structure, you need to repeat Belgium, so you have to duplicate the information. It's not a problem. Once you have the structure of the tree, you introduce the language-specific relations that we need for linearizing and resolving the arguments. And we introduce the words, the functional words that are required by the different words in the structure. So we have the these here, we have the leader of Belgium, so in English you need the of to connect leader and Belgium, etc. So now we have our syntactic trees with a subject, object, noun modifiers and stuff. Based on these relations, we'll say, like, for example, again, as I said at the beginning, the subject relation will make the verb agree with that element. The grammar will also realize the subject before the verb, the object after the verb by default, etc. No? So that's what we get at the next step for the beginning. So we have the order of all the words. So the Antwerp International Airport serves Antwerp, which be in Belgium. And the last, but the agreements here are results. We don't see them because it's on the nose information. And it generates the text like this. So the Antwerp International Airport serves Antwerp, which is in Belgium. Charles Michel is the leader of Belgium, in which the German language is spoken. So that's the actual output of the system on this input. I put again like the human generated input at the beginning. You see it's pretty similar. So it's like I'd say kind of the same quality, which is pretty good. Okay, that was for how it works. Now. There was in the past 2 years 2 challenges with this kind of generation, like a verbalization of these triples. So that's where things get a bit interesting. There was one that we've seen the data from. This is Web Energy, is called, from DBpedia triples, 373 different properties to verbalize in different contexts. Rather small data set, 25,000 data text pairs. And 9 DBpedia categories. So the one we've seen here, we've seen the triples from the airport category. Interesting fact, in this challenge, they also had a part of the test set that contained properties that were not in the training data. So the systems had to be able to adapt to unknown data. There was a second challenge at the same time called E2E. So it's the very same kind of input, but on the restaurant domain. So only 8 different properties, so much less properties, and a bigger data set, 42,000 data text pairs. So this is a gold for machine learning systems. You have loads of references for one kind of configuration. It's pretty. Lots of teams have participated in that. So these 2 challenges we have. So in natural language generation, you have 2 types of evaluation metrics. How do you decide if a system is better than another system? You have automatic metrics that I put in blue here, and human metrics. So the automatic ones, so Bleu, Meteor, and NIST, they are n-gram based. So you have a reference sentence, you have an output of a system, and you compare them word by word. You compare 1 grams, big bigrams, pairs of word by pairs of word, trigrams, and 4 grams, up to sequences of 4 words, and see the overlap between what is produced and the reference sentence. Meteor does this kind of comparison, but taking into account synonymy, allowing synonymy, not just string matching. NIST does this kind of comparison, giving more weight to less frequent n-grams. So if a sequence of words is less frequent, it probably means it's more informative. So it's more important to get them right than the frequent ones. And TR is a weird metric that just calculates the necessary post-editing that you would need to go from the predicted sequence to the expected sequence. So if you take like a word like between cat and dog, if you generate cat instead of dog and you do that on a character level, you need to change the 3 letters, no? So the cost would be 3. If you generate cat, the cost would be 0. If you generate cab, the cost would be 1. So the higher the score, the more post-editing is needed, and the less good is supposed to be your output. These automatic metrics are usually not very good at capturing exactly how good is a system. So you need human judges to judge the quality of the outputs as well, to be sure that you're doing well. So usually what is evaluated is the quality, or also called like grammaticality and semantics. So people check a text and a reference, and they say if the generated text is correct, grammatical, and if it contains information contained in the reference. So it has all the contents that it needs, and it's well put. And the second criterion, which is like naturalness or fluency, is like what's the probability that a native speaker wrote that text? So how natural it is, how fluent. It's better explained for the evaluators than I do it now, so don't worry about that. Okay, so the results. So we're going to see the results of Web Energy, so with the scene properties, which is all the properties that were in the training data and in the test set. So the system, statistical systems, have seen all the test data in the training data. So now I focused on my system here, that's at the bottom, and the Adapt and Melbourne, which are the best systems in this task. So you see that the automatic metrics say, okay, these neural systems are very, very good at learning how to generate these text from the triples. They're very good at doing what they saw in training data. See the scores, so this is out of 100, so it's 60 and a 40, it's like 20 points difference between a neural end-to-end system compared to this linguistic form, cute little system of mine. So that's a big gap. And according to the other metrics, it's also quite a big gap for this tier 1. And the one that takes into account synonymy, so that doesn't do a string-to-string comparison, see that this rule-based system gets better evaluations, closer to the neural ones, but still a bit lower. When I do boxes like this, it's because they've been tied. Okay, the organizers decided that the systems, the scores were similar, so they're tied. Okay, automatic evaluation, that's like this. The human evaluation, see, it's a bit different already. So if you give the same sentences to humans, they will tend to rank. So here you have semantics, grammaticality, and fluency, to rank the rule-based systems quite higher than in the automatic ones. Okay, in the automatic it was far from the top, and at the human one is kind of closer to the top, even in front of the Melbourne one that was doing very well in the automatic evaluation. So that's one thing. Human evaluations, they see stuff that automatic evaluations don't see. Okay, so my text is not the same as the reference, but it's still a good text that is validated by humans sometimes. Something else that you can see here is that this neural system, Adapt, is at the top for two criterions. Web energy is the text written by humans here. So people, the evaluators, they also send to human evaluations text written by humans. To see, like, okay, that's supposed to be the best, no? So this neural system managed to get more than human written texts for 2 out of the 3 criteria. And the third one is really close, 276, 273. So that's how good neural systems can be on data that they've seen. And that's, I think, it's pretty amazing. The second shared task, results are basically the same. Most of these are neural networks. And I'm this poor little guy at the end here with one of the worst scores for automatic evaluations. But for human evaluation, again, it's in there's 5 clusters of 5 groups of similar systems, and it gets to the second group instead of being like a 21st out of 22 in the automatic one. So same tendency in this second shared task. So conclusions, yeah, automatic evaluations here. Neural systems are much better than rule-based, at least in this case, than this rule-based. And in human evaluations, they are still better, but I would say only slightly better. Remember before this slide, I told you like web energy also in the test set, half of the test set contain data that was not seen in the training data. So that's a challenge for the neural network systems because the inputs contain stuff they have never seen before. Some stuff they have seen, some stuff they have never seen. So they just try to guess. So the results here are here on these unseen properties only. Okay, the properties that the systems haven't seen. See that now the rule-based system is at the top for the automatic evaluations and the human evaluations. So it ranks first in all evaluations. And you see that the system that was amazing at mimicking doing the generation on known data, Adapt, collapses on unknown data. But the Melbourne that was a bit lower than Adapt on the known evaluation doesn't fall as much. No, it's actually quite close to the rule-based system. So there's a trade-off between how you can optimize the system for a certain data set and how to leave it open for unknown properties. This is the overall evaluation containing all known and unknown properties, and you see that on the overall with the test sets of similar sizes, the linguistically informed system, that this rule-based system gets the best human evaluations of all the systems, and is quite also still a bit lower on the string-to-string comparison metrics and even beats them when synonymy is taken into account. So in this case, you see that you can see a bit like the good point of these rule-based systems. No? So that's my intermediate conclusions, and they're really close to the actual conclusions actually. Is that what we see now, a linguistically informed energy system can more than compete, I'd say, with neural network implementations, at least in some tasks. So now we've seen verbalization of structured data. It's true for this kind of data. It's not true for other tasks. No? If you, in parsing, statisticals are much better. In other types of generation with very wide variety of inputs, the neural networks are much better as well. But for this kind of generation, the rule-based can compete. The second point, the second conclusion here is that the linguistic information encoded in the energy system that I showed you before can be reused. So you saw that I could get very nice results on the unknown properties because I had 2 hours, like people had just a few hours to adapt their systems to the unknown properties. The statistical systems could not be adapted because there was no training data. And my system could be adapted in a couple of hours to 100 new properties. And I got almost the same results in the unknown and in the known properties. So these rule-based systems can be reused, so for a new domain and also for solving new tasks. And that's what I wanted to show afterwards. We'll go very fast on that. So the knowledge that's encoded in the generation grammars, this knowledge, this very same knowledge, can be used for doing the opposite step, which is the analysis, semantic analysis of sentences. So I have 5 minutes left. So I had planned a small section on that, but I'll try to give a very short overview. The idea of using grammars for analysis is, first of all, you can use them in analysis pipelines, so in conversational agents or similar systems. You need some semantic analysis modules, and also this kind of tool can be used to create training data for energy systems. So right now, until last year, there was no multilingual data set for training natural language generation systems. You've seen the 2 shelters that I showed you, Web Energy and E2E, they were on English only. Because there's only data for English. It's a very new field, this natural language generation, so there's lack of data. Annotating data manually is very costly. You cannot, I've done that also for a few years. It's very painful and not very rewarding. So you want to avoid annotating manually if you can. And one way to go around that is to create automatically data sets using, again, graph transaction grammars, for example, using like rules to derive semantically annotated data sets from syntactically annotated data sets. So we also created a task for that. The point is, okay, this is the kind of data that exists. I'm sorry, it's very slow again, very small again. This is a syntactic annotation of a sentence in the universal dependency corpus, which is a big data set that contains about 200 data sets of 150 different languages. So this with kind of normalized annotation. So you can use this big tree bank of multilingual data to create data for generation as well. This data set in the first place was thought for training parsers. So you have this one word per light format. So this is the third was being run by the head of an investment firm. So you have the third was being run by the head of an investment firm. So for each word has a lemma. Okay, so was is B. You have the coarse grained part of speech. You have fine grained part of speech, a grammatical category. Then you have morphological information, and then you have information about the dependencies. So the first line here, the is governed by word number 2 with the relation det. So you see the governed by word number 2 with the relation det. So all this information here is available for many languages. So what we did is creating from here inputs for natural language generation. The simplest one you can do is to, for example, train linearizers and morphological realizers. So for that, you just need to scramble the structure here, poop poop, and get a tree that's not ordered with no surface forms, and ask people, okay, now your task is to order the words and resolve the morphological interaction between the words. And then from the same sentence, you can go even deeper and start from this abstract representation with the third run head firm investment, like run being the main predicate. So yeah, see the head of a firm investment runs the third. So it can be said in one way or another. And here in this case, you have lots of more transformation to do. That's the ones that we've seen before in the pipelines. The thing is to create the whole data set, you have to do all these steps. Now first, randomize scrambling, then replace the words by dilemmas. This is pretty much straightforward. It's very easy. You can do that with a Python script. It's very simple. But then removing functional propositions, which is the opposite of adding them in generation. Replacing determiners, auxiliaries, and models by attribute value pairs, which is again the opposite of what we do in generation. Removing copulas, the empty Bs, again the opposite of what we do in generation. The removal of subject and object relative pronouns, generalization of the edges, the removal of the information, morphological information, and the removal of the fine-grained part of speech tags. All this can be done by graph transaction grammars, again, that have the same thing, that same knowledge as the generation one we've seen before. So if you do generation grammars, you can reuse the knowledge for the opposite task that can be used for a pipeline system or for creating data sets like this. If you're interested, I can show you the rules later. So the conclusions is, I'm going to repeat myself a bit, sorry. The linguistic information encoded in a rule-based analogy system allows for high-quality generation from structured data. We've seen that with the evaluations. This can be reused to adapt the generator to new domains and new languages. We've seen that on the evaluation of the unknown data in web energy. And can be reused for other NLP applications, as we've just seen now. Right now, most neural network generators do not use linguistic information. So their portability is limited, unfortunately, for now, in terms of domains and languages. But we've seen that they're capable of imitating human writing very, very faithfully, actually amazingly faithfully, and on a large scale with no coverage issues. So in the end, I'd say like it's, yeah, now since this makes it very tempting to use neural network systems, I think in any domain. But I hope I convinced you a bit today that that is always a good reason to leave some room for linguistics. Okay, so thank you very much.
Okay, guys. Does anyone have questions?
What's the situation with non-English texts, non-European texts?
You mean the generators? Non-European, like Russian, for example, or what? Chinese? There's not much work on that. That's why last year we started doing new data sets to foster a bit the development of tools like this. But so last year, for example, in the share task we had Arabic and Russian as languages, but only for the linearization part and morphological interactions, so not from deep structures yet. But this year in the share task, by the way, it's still open. If you want to participate and have a play with the data, you just can contact me or go on the web page. So this year there's again Russian and Arabic, and we also put stuff like Hindi, Korean, Japanese, and Indonesian. So to also try to get languages that are not European, because I think most of the work is being done on European languages, indeed, yeah. So that's, and I've just done actually a deep parser of Chinese now in a couple of weeks ago. So we have now a deep data set for Chinese as well, UDs that could be used. We haven't thrown it in the share task yet because I want to check it first, but it's being
In general, there is no structural obstacles to that.
no structure of?
There is no structural problem of generalizing it to another language.
I don't think there's problems. No, it can be. I mean, it can be more or less complex, but you can always do it, I think. Especially with rules. Yeah. No, like in this task in particular, no, there's no context at all. I mean, there's no context for my system, for example. There's no context because I just see the triples, and all the systems that the share task are the same. They see the triples only and do generation from there. But some systems also have, it's been recently implemented, they have a memory component that at the time they're training, they also memorize information. And if they had to generate from these 4 triples that we've seen, they could have generated 10-line text with the information that they memorized during the training. So it is also being done. I think it's a new topic as well, but it's starting to emerge.
Do you guys have room for one quick question? Yeah, maybe small. I'm like, I understand that it's kind of like a dumb question that I'm like, that's your presentation was all about, right? But and you probably heard it a lot. But I'm like, in case you have to convince me, like as a young researcher, to not to go, like straightforward to like pure like neural networks without like any linguistics. So if you have to convince me, like in just like maybe a couple of sentences and try to say that your kind of approach with linguistics embedded is really cool, what's gonna be the
I don't think I would try to convince you because I don't think it's possible. I think like people who want to do neural networks, they will do neural networks, and that's has nothing to do against that, I guess. So good for that because we need that. It's great for solving some tasks. I would convince you to, while doing neural networks, take care a bit about linguistics. Look at what you are doing and look at the task and at what you have in the data. Because I see people that do great. The guy who does ADAPT, the ADAPT system is a great system. We've seen that got better results than human sentences, when judged by humans. This guy doesn't know much about linguistics or anything. He doesn't know what is happening in the middle. He optimizes the system for a task without really knowing what it is. And in the end, when they have questions, they come back to the linguists. So if you want to avoid to resort to linguists and stay away from them, which can be good for the neural network people, do a bit of linguistics yourself. And and also I think it helps a lot. Also, if knowing the linguistics, knowing what's behind the tasks that you do, it helps you model the problem much better.
Okay.
So just for that reason.
Okay, cool. Yeah. So thank you.
Thank you.